Thank you. The most important thing to tell you about this talk is that I'm not at all sure what I'm going to be saying is correct. I considered whether it was therefore my duty to cancel the lecture. It was tempting, but I justified giving the talk to myself on the grounds that you might learn something from what I was trying to do, even if it turns out that my proposal isn't right. So, since it's trivial classically, it's reasonable to hope that you at least might be able to solve it quantum mechanically, and maybe you'd be able to learn something from the exact solution. So, it's been studied from many points of view by people who hoped to, in this way, get a soluble model of quantum gravity, but nevertheless, the status is fundamentally unclear. I don't know whether that's the right interpretation, but in any event, since I don't know any precise observables, I can't try to solve 2+1-dimensional gravity with positive lambda, since I wouldn't know what to try to compute. So we can simply say what it means to solve the theory for negative lambda. What it means to solve it is to find the dual conformal field theory. Now, this formulation makes obvious a statement that from a classical point of view looks rather surprising. When we look at the classical action, it appears that L, which is the cosmological constant essentially in Planck units, is a free parameter. But the formula for the central charge shows that this must be wrong. According to the Zamoychikov-C theorem, in any contiguously variable family of conformal field theories in 1+1 dimensions, the central charge C is a constant. Hence, it cannot depend on a variable parameter such as L over G. It must be that 2+1-dimensional quantum gravity makes sense at most only for certain values of L over G. But what are the right values? Actually, until here, I think everything I said is true. It's past this point where I offer no assurances. We're just going to take at face value the gauge theory description of 2+1-dimensional gravity, although we don't really know why we should do this, since we don't trust it non-perturbatively since it doesn't describe the black holes. Now, one simple fact is that the ground state of such a theory is minus c over 24, which is minus k. Now, if there were no other excitations, the partition function in genus 1 would be this thing. Now, although it's a nice function, it can't be the full answer because it's not modular invariant. So there have to be some additional states. It turns out that the largest you can make L is k plus 1, and if this is the right value, then the partition function is uniquely determined. In fact, something nice happens. Just for fun, if k is 1, the partition function is the J function itself, and the black hole entropy is therefore the logarithm of 196883, which is 12.19 approximately. So this is really the worst we're going to do, and it will only get better from there as we approach the classical limit. There's a close analog of this in the supersymmetric case. So I guess I'm going to let you off the hook a little early today because I know you've been grossly overworked this week.